Good afternoon. Science matters. It matters not only for understanding the technological underpinnings of our society, and not only as a cornerstone of rational thought, but also for appreciating the universe, the way it works, and our place in it. Accordingly, 8 research centers of the College of Arts and Sciences have banded together to present this series, Science Sundays. I'm John Beacom, and I'm representing the Center for Cosmology and Astroparticle Physics. Because of the sustained interest in this series, which has grown over time, we're delighted to see that, we've been able to attract better and better topics and speakers. And today, on behalf of CCAP, I'm very pleased to present Dr. Joe Lykken, who is the Deputy Director of Fermilab, the largest particle physics laboratory in the United States. He's also the Chief Research Officer. Joe will tell us about what's going on in particle physics, and he'll be happy to take questions at the end. And after that, we'll all go upstairs for a nice reception where we can talk to Joe further. Let's welcome Joe Lykken.
Thanks, John, for that nice introduction. As John said, I'm a physicist, particle physicist from Fermilab. I've been working there for 25 years, mostly doing theory, but I joined the CMS experiment, which I'll talk about a little as we go along. And so I'm not quite an experimentalist, but at least they'll tolerate me in the room, although they won't let me touch anything. I'm going to give you a brief introduction to Fermilab itself, and then we'll talk about some of the science that we're doing there. And I won't be able to talk about everything we're doing, but hopefully enough of it that it'll get you interested, and we'll get some questions, and we can talk more. So let's start with Fermilab, where it is. There we go. So this is Fermilab. It's not that far away. It's only a 108-hour walk, according to Google Maps. It's outside of Chicago, as you can see. It used to be surrounded by farmland, but Chicago in the last, Fermilab was founded 50 years ago, and in those 50 years, Chicago has expanded westward and absorbed Fermilab. However, it still is one of the biggest collections of green space. So this, if you're flying into O'Hare, you might see a view that looks something like this. So this is Fermilab. And as you see, it looks like a big park, or a combination of natural space and a little bit of farmland. And the only weird thing is that you have 2 big circles here. These are particle accelerators. They're actually underground, but this is what you're looking at is the roads, and we actually have circular rivers to help cool the big magnets that are in the particle accelerators. But other than that, it's a big green space. If you come and visit, which you can because we are one of the only open national laboratories in the country. In fact, there's not even a fence around Fermilab, so you can come anytime you want and visit. And if we get a lot of bird watchers because we have a lot of birds, as you can see here. This is a selection of birds, including the Canada geese that we don't really like, but they're there. But it's a good place for birds. We're a good place for bison. We have our own bison herd. They have cute babies. We occasionally get them to stampede, but they don't really like to stampede because they're kind of lazy. But it's exciting to see that when it happens. And these are genetically pure bison. We had them tested a couple years ago to make sure that they weren't really cows, but they are actually pure American bison. So that's what it looks like at Fermilab. And then we have a lot of people at Fermilab doing science, and this is a selection, not a biased selection of neutrino scientists. And that's one of the things I'm going to talk about today, but it's not all that we do. But it's one of the things we're excited about, and there's a whole collection of YouTube videos. If you want to see a lot of people talking about neutrinos, just go to YouTube and say Fermilab neutrinos. And that's part of what I'm going to tell you about today. More generally, we're doing a whole bunch of different experiments that are involved with different aspects of particle physics. Besides neutrinos, we're studying the Higgs boson, which is not something we can do at Fermilab, but we do that with our colleagues at CERN, which is an even bigger particle physics lab, which is on the Swiss-French border, where we have big experiments there. I'll mention those. We're also very interested in dark matter and dark energy. It turns out most of the universe is actually made out of this. And as you can see from the names, we don't have a super good idea as to what either one of those things are. So these names are placeholders for something that constitutes 90% plus of the universe is whatever these things are, and we don't know. So one of the messages I want to give you here is that the things we're studying are very fundamental to the universe and how it works. All three of these, all four of these that I've listed here. And they're related to each other, and one of the things we're trying to understand is how's the Higgs boson related to neutrinos? How is dark matter related to the Higgs boson? We think there are relations there, but we haven't figured that out. And the other thing is that they're very difficult to study. Why don't we already know everything about these things? Because they're very, very hard to study. The Higgs boson was not actually manufactured in a particle accelerator. It was done at CERN 5 years ago. Neutrinos, I'll tell you a little bit about the story of the challenges of how to detect those. They've been detected, but they're very, very hard to detect. And nobody has detected dark matter or dark energy in a laboratory experiment. So these things are very hard to study, and that's why we know so little about them. And it's one of the big challenges of this field. And the other thing I wanted to emphasize is that in particle physics, what you're always doing is you're exploring the unknown. So this, if you like, is the known unknowns. But we're always looking for new things, new particles and forces that can pop up out of nowhere, extra dimensions of space. Who knows? There's all kinds of things that could show up in our experiments and maybe will show up in the experiments. But we can't even make a list of all those possibilities because we probably don't have the imagination to do that. So this is the physics lecture. I'm going to start the neutrino part of this lecture by reading a poem. This is a poem by John Updike, who's better known as a novelist. But he wrote a poem in 1960 that was published in the New Yorker magazine called Cosmic Gall. And this is in the very early days of understanding neutrinos, but it's a very interesting depiction of what we knew, at least in 1960, about neutrinos. So I'm going to quickly, I've edited it for content, but I'm going to quickly read the poem. Neutrinos, they are very small. They have no charge and have no mass and do not interact at all. The Earth is just a silly ball to them through which they simply pass. They snub the most exquisite gas, ignore the most substantial wall, and scorning barriers of class, infiltrate you and me. Like tall and painless guillotines, they fall down through our heads into the grass. So, good poem. But I'm a physicist, so I'm now going to deconstruct this poem and criticize the physics behind it, because that's what we do. So, first of all, he says neutrinos have no mass. In 1960, this was believed to be the case. So if you went and did a poll of physicists, 100 out of 100 would have told you, yes, neutrinos have no mass. But we now know, due to some very heroic experiments that I'll touch on in this talk, that they do have masses, but their masses are very, very tiny. They're less than a millionth the mass of the electron, which is the next lightest particle after neutrinos. So that's a big mystery. We don't understand why they have mass, and we don't understand why they have teeny, teeny, tiny masses. He says they do not interact at all. So even in 1960, that was known not to be the case. So this is artistic license on his part. But they interact very, very, very weakly, and I'll talk about that in a minute. The Earth is just a silly ball to them through which they simply pass. This is due to an excellent approximation. About 1 in a billion neutrinos going through the Earth will interact with the Earth, and the rest just go right through. And similarly, with you and me, they are neutrinos from a variety of sources that I'll talk about that are passing through your body right now. There's more than 1 trillion a second going through your body right now, whether you like it or not. But they don't do any harm. And in fact, the chance that even a single one of those neutrinos will do anything at all inside your body during your entire lifetime is about 1 in 4. So they really, really do not like to interact with the kind of stuff that we're made out of. They are, however, elementary particles, as nearly as we can tell, and so we can put them in the table like this with the other elementary particles. So you are not made out of neutrinos. These are the 3 kinds of neutrinos we know about. You are made out of this, this, and this. Why there are other elementary particles we don't really know. Some of them have to do with forces of nature. These have to do with photons, have to do with electromagnetism. This has to do with nuclear force. All 3 of these have to do with nuclear forces that have to do with radioactivity. So we kind of understand why they're around. We have no idea why these other quarks are here. We have no idea why these relatives of the electron are here. And we have no idea why the neutrinos are here. And this is part of what we're trying to understand. Neutrinos are produced by lots and lots of different sources, and that's one of the things that tells us neutrinos are important. They're produced by the sun and the nuclear fusion processes that power the sun. And in fact, nowadays that we have big neutrino detectors, we can actually see the sun, not in light, but in neutrinos. And this is reconstructed electronically from neutrino detectors, but nevertheless, this is an image of the sun as seen not in light, but in neutrinos. So a lot of neutrinos from the sun. Lots of neutrinos are left over from the Big Bang. And this is just the statement that neutrinos are part of the matter that was formed in the Big Bang. And in fact, there were more neutrinos produced in the Big Bang, we think, than any other known matter particles. So there's lots of neutrinos from the Big Bang. They're produced when stars explode in supernovae, and I'll come back to that later on. They're produced in our atmosphere and the cosmic rays, which are high-energy particle interactions in the atmosphere. They're produced by nuclear reactors. They're produced by nuclear processes inside the Earth, so uranium and thorium decay and produce neutrinos. And they're produced by bananas, and therefore also by your body. This is from an isotope of potassium, so of course you have potassium in your body. Bananas have a lot of potassium. Avocados, I'm told, actually produce twice as many neutrinos as bananas, so if you really want to make neutrinos at home, you can buy some avocados. Okay? So conclusion of that is that neutrinos, first of all, they're really important. They're involved in all kinds of very fundamental parts of the universe, from the Earth to the Sun to the Big Bang. They're weird, and I've already mentioned a couple weird things about them, and I'll keep talking about the weird things. And they're everywhere, and we think they're connected to everything, and part of what we're trying to understand is, what is that connection to everything? So now I'm going to give you just a little bit of history. I'm trying to do mostly not history in this talk, but some of it I can't resist, especially the history that has to do with Enrico Fermi, since Fermilab was named after Enrico Fermi, of course the famous Italian-American physicist. So Fermi, although he didn't have the original idea of the neutrino, that came from another physicist named Wolfgang Pauli, but he made the first theory for neutrinos and what they might be doing. And this was in a paper that he wrote in 1932, where he proposed that a particular kind of radioactive decay process that physicists were trying to understand, called nuclear beta decay, actually involved a new force of nature. So that's already a big deal, new force of nature, which he called the weak interaction, which is what we still call it. And this new force of nature involved, he thought, neutrons, protons, electrons, so these are all the familiar particles that we're made out of, and a new invisible particle. And the new invisible particle he called the neutrino. It was actually one of his Italian colleagues came up with the name as a joke, but he thought, oh, it's actually a pretty good name. And so he's the one that named these invisible particles neutrinos. This is a brilliant paper. It's one of the most brilliant particle physics papers anybody ever wrote. He knew it was a brilliant paper. He submitted it to Nature, which is the most prestigious physics journal, assuming that they would accept it. But in fact, they rejected it. And they rejected it because it contained, quote, speculations too remote from reality. So let that be a lesson to all the budding scientists out there. Just because it's brilliant doesn't mean it will be immediately recognized, at least, as brilliant. And the speculations too remote from reality were the invisible neutrinos, presumably. The weak interactions, I mean, they knew that there was something making this happen. So I think the neutrino part of it was more controversial than the fact that there might be a new kind of force. Almost immediately after Fermi came up with his idea, he was talking to these guys, the two other brilliant physicists, and they realized that his explanation for nuclear beta decay, which in more modern language we would talk about as a neutron turning into a proton, an electron, and these funny neutrinos, they realized you could rearrange this process and make a process that would actually detect neutrinos. So suppose neutrinos are coming into this room, as we know they are. They said, well, they could react with the protons, which are in the material in this room, and every once in a while, they would convert that proton into a neutron and into the antiparticle of an electron, which is called the positron. And these are pretty weird things. They're not around very much. And therefore, even if this happened only very rarely, there's at least some chance you could do an experiment that would look for the production of a positron with a neutron. And then they estimated the rate at which this would happen, and it was a correct estimate of the rate, and they concluded in their paper, there is no practically possible way of observing neutrinos, period. And so they had the right number. It's just that they were overly pessimistic about the ingenuity of humankind and our ability to make technological advances. However, this was in the 1930s, and it was indeed not until the 1950s that anybody in a serious way went back and looked at this and said, how could we actually detect neutrinos this way? And the first people to make a serious proposal were Fred Reinus and Clyde Cowan, who said, well, I know a way to make a lot of neutrinos. It's called a nuclear explosion. And they were physicists working at Los Alamos at the time, where they were looking at nuclear tests. And so they actually proposed this setup, which was to try to detect neutrinos directly as part of a nuclear test. I'm not quite sure of the details of the history, but they were talked out of doing this. It's actually not a super easy thing to try to do. And what they did instead, their backup plan was, well, another good way to make neutrinos, as I already mentioned, is to use nuclear reactors. And so they went to the Savannah River nuclear reactor, and this also was very, very difficult, and the first try actually didn't work, but they eventually were able to show that they were producing this process, and presumably because of the fact that neutrinos were interacting with matter in their detector. And in fact, Fred Reinus eventually got the Nobel Prize. Cowan, unfortunately, didn't live long enough to get his prize. So that was the first detection of neutrinos, 1956. Now, as I said, there's three kinds of neutrinos we know about. The second kind of neutrinos was discovered in 1962, and at this point, we're now talking not about nuclear reactors, but about people using particle accelerators, in this case, a proton accelerator. This is very similar to the kinds of things we do at Fermilab. So this is sort of the more modern age of doing neutrino physics with accelerators. And in fact, one of the three guys that won the Nobel Prize for this was Leon Lederman, who later became director of Fermilab. So again, Fermilab connection. So that was good. And in fact, the third kind of neutrino that we know about was discovered in 2000 by an experiment at Fermilab. Unfortunately, by this time, they were not handing out Nobel Prizes, apparently, for discovering neutrinos. So the best they were able to do was to become a question on Jeopardy, which is a kind of fame. I think the real problem here is that in the modern age of particle physics, things are done by big collaborations. This is not actually a big collaboration. It's pretty small by modern standards. But they don't hand out Nobel Prizes typically to collaborations like this. But nevertheless, they found the third kind of neutrino. So those are the 1, 2, 3 kinds of neutrinos that we know about. Well, so that's, if you like, proving that neutrinos exist. But what do they do? What are their weird properties? What's interesting about the neutrinos? What can we learn about neutrinos? That also has a very interesting history that I'm just going to zip through very quickly, because it turns out this history is also part of our future for neutrinos. And this part of the story starts in the Homestake gold mine, which you might have visited. It's in Leeds, South Dakota, in the beautiful Black Hills of South Dakota. This is one of the, where one of the shafts are that go down. It goes down more than a mile underground here. It was the largest gold mine in North America for many years. They took $40 billion worth of gold out of this mine. But it's also a good place if you want to get away from the natural radioactivity of cosmic rays that are, for example, in this room, and you want to do a very sensitive experiment looking for something like neutrinos. So in fact, way back in the 1960s, this guy, Ray Davis, had the idea to go down in the Homestake mine, take a big tank down there and fill it with liquid, which is basically chlorine, and then try to do a detection of neutrinos using, in some sense, this is a chemistry experiment. You take a big tank of chlorine and you look to see whether at the end of every year, whether you've got a couple of nuclei of argon, which is the different element that could be produced if neutrinos from the sun are interacting with the chlorine in your tank. So that's a very clever idea to detect neutrinos. This is something you can do with a lot of precision. So he started this in the 1960s. He got a few of these every year, and he just waited patiently and kept doing it and counted them to see how many solar neutrino induced events he could detect. So this is not very interesting unless somebody goes out and predicts how many solar neutrinos you should detect. And this was led by a theorist named John Bacall. And this is actually a very difficult calculation because most of these neutrinos that he's detecting are coming from very complicated processes in the center of sun that involve nuclear fusion, and which you might have thought we didn't know well enough in order to make a good prediction. But nevertheless, Bacall made the prediction that Davis's experiment should detect 36 solar neutrinos per month. And in fact, Davis, over the course of many, many years, only detected about a third as many as were predicted. So this now takes us to the 60s, 70s, and 80s, at times when I was alive, at least the latter part of that. And so I remember what people thought. And what people thought, including me, is they thought, well, either Davis's experiment is wrong, or Bacall's theory prediction is wrong, or they're both wrong. Those were the only possibilities that people really took seriously. Because it just didn't make any sense. You know, it's much easier to believe we don't understand the sun in detail than it is to believe that you could be so wrong about the number of neutrinos coming from the sun. But in fact, they were both right. The sun does produce what would have been the equivalent of 36 neutrinos. And the reason you weren't seeing them is because something was happening to those neutrinos after they were produced inside the sun. And this was confirmed much more recently. It was around 2000 by two experiments, one the SNOW experiment in Canada and the other Super Kamiokanda, which is based in Japan. And they confirmed that, in fact, Davis was right and Bacall was right, and that the resolution of this was that neutrinos are very strange. And how are they very strange? They're produced inside the sun in one of the particular flavors of neutrino that I talked about, these electron-type neutrinos. But by the time they get to the Earth, they have become a mixture of the three flavors of neutrinos that I talked about. And this is a very strange thing for elementary particles to do, because remember, elementary particles are elementary. They're supposed to be their own kind of thing, not some other kind of thing. And so why, after they're produced in the sun, do they go from one flavor to essentially an even mixture of three other flavors? This is something that is not supposed to happen in elementary particle physics. So one of the conclusions of that is that neutrinos have mass. Remember I said we discovered that neutrinos have mass. And this has to do with an explanation for why they can change flavor, but it's an explanation which nobody in this room will find very satisfying, because it depends on quantum mechanics. Quantum mechanics, remember, has well, you may not remember, because I'm not assuming you all know quantum mechanics. But quantum mechanics has all kinds of weird statements like this, that you can be kind of this thing and kind of the other thing, but you can't be both things at the same time. And applied to neutrinos, what it says is neutrinos have mass, and they can have a particular mass, and neutrinos have what I was calling flavor. They can be of a particular type, but they can't be both of those things at the same time. So you pick, you can have a neutrino with a definite mass, but then it doesn't have a particular type. Or you can have a neutrino of a particular type, but then it doesn't have a particular mass. So that's not very satisfying, because it's the weirdness of quantum mechanics, but we do believe that that is the beginning of the explanation for what neutrinos are doing. They have very strange quantum mechanical properties. So that's about, it's not all you can do with neutrinos coming from the sun. In fact, we were actually talking about this at lunch. There's interesting things we can do in future experiments with solar neutrinos. But really, most of the action in neutrino physics is shifted to things that you can produce using accelerators. And in particular, at Fermilab, we're able to make beams of neutrinos, which is not easy to do. And we're, at the moment, making two beams of neutrinos. One is called the booster neutrino beam, which is green, apparently. And the other one is called the NUMI beam, which is red, apparently. And they're produced using different parts of our particle accelerator complex. Our particle accelerators don't accelerate neutrinos, they accelerate protons, which are much easier to get a hold of and accelerate. But from those beams of protons, we're able to make beams that are essentially pure beams of neutrinos. And in the future, we're actually planning to construct a third beam of neutrinos called the DUNE beam. So that's good. We're actually able to do then laboratory experiments based on beams of neutrinos. Here's the biggest one that we're doing now. So we produce a beam of neutrinos in Fermilab. We shoot it into the Earth in such a way that it comes out of the Earth more or less 500 miles away in northern Minnesota. Up in northern Minnesota, we have 15,000 tons of this, which is a kind of material called scintillator, which is one of the ways that you can detect neutrinos. Why do we have 15,000? So this is a person, to give you the idea of scale. So why do we have 15,000 tons of stuff? Because if you don't have enough mass, you don't have enough chance of detecting any neutrinos, because they so rarely interact with ordinary matter. So you need very large mass in your detector, and then it better be something pretty cheap, because if you needed 15,000 tons of diamond, even though that might be a good detector, you probably are not going to get funded by the government to do that. So in this particular case, we use essentially a kind of plastic material that's cheap, and so you can make large amounts of it and make a detector. So why are we doing that? We're doing that because we're then able to send these beams of neutrinos up to northern Minnesota. We know what they look like when they left Fermilab. We know what kinds of neutrinos they were. And then we find that when they get up to northern Minnesota, every once in a while you see a little blip in the detector that looks like this. This is an actual neutrino-induced event. This is not the neutrino. The neutrino came in, and then it did something. It interacted with the detector, and then we're able to interpret what this blob here is in such a way as to understand what the neutrinos are, and in particular, what kinds of neutrinos we're seeing when they get to Minnesota. So this is very unusual for particle physics. You normally think of particle physics as involving microscopic properties, and therefore you do microscopic experiments. These are microscopic physics in some sense, but this is 500 miles. So you're combining things, very small things, with very large distances. Very unusual. Also, this 15,000-ton detector has an awful lot of cosmic rays going through it. So if you actually look at a picture of what the detector is seeing at any given moment, it's seeing this. You see all these streaks going through the detector. Almost all of this is cosmic rays that's coming in from the atmosphere, and it's not the stuff we're interested in. So one of the big challenges of these kinds of experiments is how do you tell the difference between all this junk and the neutrino things that we're actually interested in? And some of our brilliant young physicists realize that this is the kind of thing where it's good to use the kind of techniques people now use in artificial intelligence to do things like identify cats in YouTube videos. This sort of computer vision, identifying things in an automated way that a computer program, it turns out, can do better than a human being. And indeed, we have now found that we are able to, by using this kind of deep learning, machine learning, artificial intelligence techniques, we're able to find the neutrinos here better than a human being could do by eye or by any of the techniques that we knew before. This is very important for neutrino physics because being able to detect the real neutrino events from all the cosmic ray junk, say 30% better, which they've already done, that's the equivalent in what I was showing you to adding 5,000 tons to the detector. And that's a lot of money to add 5,000 tons to your detector. So geniuses are much cheaper than buying detector, is the conclusion. The other thing we're doing is trying to look at different kinds of ways of detecting neutrinos. So this is looking down, this is at Fermilab, looking down into a tank which has a clear liquid which looks kind of like water. And in fact, if you look at it, it looks like water. But it isn't, it's liquid argon. And it's much colder than water. It's minus 300 degrees Fahrenheit. And liquid argon turns out to be a very, very good material for detecting neutrinos. Here's, this is actually a 200-ton detector we have operating at Fermilab now called microboon. I don't know why it's called microboon because 200 tons is a lot of liquid argon. But as you see here, when the neutrinos interact with the liquid argon in microboon, they actually produce much more complicated looking junk than what I showed you from the NOVA experiment. And that's a good thing because that means there's more information here than there was in the event I showed you from the NOVA experiment. And our physicists know how to interpret all this extra information, and that allows you to do a better neutrino experiment by using this kind of technology. So this is being led by Bonnie Fleming, who's a professor at Yale, and this is the beginning, we think, of a whole new frontier, if you like, of doing neutrino physics with liquid argon-based neutrino detection. Something very challenging to do. I should say, by the way, it's not just a tank of liquid argon. You then have to put plates at either end, and you charge the whole thing up to 100,000 volts. So it's 200 tons of liquid argon with 100,000 volts going through it. So these are not trivial devices. Another thing we're doing at Fermilab right now, which seems like it has nothing to do with neutrinos, but is related to them in a very profound way, is we're looking out at the universe. So I talked about neutrinos coming from the sun. There is a big universe out there doing all kinds of crazy things on the scale of galaxies and the whole, what's left over from the Big Bang. And we have telescopes looking at that too. And how is that related to neutrinos? Here's how it's related to neutrinos. These are computer simulations of the whole universe. And they're made by saying, okay, there was a Big Bang, I had a bunch of stuff, I think I know what the stuff was more or less. And now I have the computer turn the crank and let gravity do its work. And what gravity does is it makes the stuff, which in the Big Bang was uniformly distributed, it makes it clump together. And that's what these dark colors here represent matter, which over time, billions of years, has clumped together from the force of gravity. And so they run this simulation, and they do it in two cases. In one case, they do it where the neutrinos are in there, but the neutrinos don't have any mass. And then they do it again, the neutrinos in there, but the neutrinos now have a small mass, similar to the mass that we think they actually have. And you can see by eye that these universes are not the same. This universe is fuzzier. It's not as clumpy as the universe in which neutrinos don't have any mass. So turning that around, if you could actually observe the real universe in enough detail, you could tell something about what the mass of neutrinos is and compare it to what we get in experiments. To me, this is an absolutely amazing thing, that the actual shape of the universe on the largest scale, this is billions of light years. This is the whole universe, billions of light years. The shape of the universe on the scale of billions of light years cares about the mass of neutrinos. That's one of the things we're trying to understand. So how do you do that? You have to look at the shape of the universe. You have to look at something out there that cares about the shape of the universe on the scale of billions of light years. And it turns out one of the easiest ways to do that, there isn't any really easy way, but a way to do that is to look at something called the cosmic microwave background radiation. And here, the key word here is microwave. It means you have to look out at the sky, look out at the universe, not in light, but in microwaves. So for that, you need a telescope, but it has to be a telescope that sees microwaves instead of optical light. I don't know how you build a thing like that. I really don't know how you build a thing like that. But we have people that do know how to build things like that, in particular Brad Benson, who's leading our effort at Fermilab, working with lots of other physicists and other labs. And they designed a microwave telescope, a state-of-the-art microwave telescope, in order to look out at the sky and see if they can see some of this structure that's sensitive to neutrinos. The other thing you have to do is you have to put that telescope in the right place, and it turns out the right place to put it is the South Pole. So no problem. So last year we built this thing, we tested it out at Fermilab, we said, okay, it's good. We stuck it in a bunch of crates, and we shipped the crates to the South Pole. And then we sent our people down there. So here's our people at the South Pole. This must have been a warm day, I guess. And then they installed it here, and this is the microwave telescope that we're operating at the South Pole. And this has about 20,000 individual microwave sensors that are looking out at the universe. And eventually, this is going to tell us something about neutrinos just by looking at the universe. So completely independently from the accelerator experiments that I was talking about. And this is just nature. This is one of these weird connections of nature that we sort of don't deserve, but we're going to take advantage of. So now I want to talk about the future for neutrinos before I move on to other things. So what is the future? Well, part of the future has to be to do better experiments, because even those really ambitious experiments I just showed you are not good enough. And in order to understand what neutrinos are really doing, we need, for example, better beams of neutrinos, which means better particle accelerators. And we need better ways to detect the neutrinos, larger, more sensitive neutrino detectors. So that's, for Fermilab, this is a big part of our future, and I'm just going to briefly describe that. And it turns out that takes us back to the Homestake Gold Mine, because the Homestake Gold Mine is a really good place to put neutrino detectors. It's about 800 miles from Fermilab. So again, here's Fermilab. I showed you the experiment that goes to northern Minnesota, and we now want to make a different neutrino beam that goes to the Black Hills of South Dakota and put detectors in. The Homestake Gold Mine is now owned by the state of South Dakota. It's not operating as a gold mine anymore. But we want to put our detectors in the former Homestake Gold Mine about a mile underground. So that looks something like this. You have an accelerator at Fermilab. You make neutrino beams. You point them down into the Earth, because remember, the Earth is round. So if you want to go to South Dakota, you don't go that way. You've got to go that way. And then when it gets to South Dakota, you're going to have your detectors underground. And the farther underground, the better in some sense. And we have a place in the Homestake mine that's about a mile underground where we're going to put neutrino detectors. And this new experiment, which doesn't exist yet, but we're starting to build it, is called DUNE, which stands for Deep Underground Neutrino Experiment. This requires a lot of time, a lot of expertise, a lot of money, and a lot of really smart people. So this is the kind of thing where you need a global collaboration. It's not, the US can't do it by ourselves. You need the whole world to help you. We have so far 31 countries, 176 labs and universities that signed up to work on this, 1,000 physicists, including young people. These are just some of the young people working at Fermilab on neutrinos. These are the people that actually do the experiment, because by the time we do the experiment, it's going to be 10 years from now. These things don't happen overnight. So it's going to be the next generation of young scientists that do all this. And I actually spend, in my management job, I spend a lot of my time going around to these various countries to talk to the physicists there and help them get money from their own countries in order to do this stuff. I was just, in fact, last month, I was in Medellin, Colombia, talking to funding agencies in Colombia to help our Colombian physicists get money. So why are they doing this? What's interesting about that? Well, rather than give you a physics lecture, I'm going to give you a nice little video that we put. It's only 2 minutes long, and it has much better narration than I can do, and it tells you everything you need to know. Hopefully the sound will work.
13.8 billion years ago, the universe started with the Big Bang. Energy transformed into matter and antimatter. But what happened next? According to discoveries made by Albert Einstein and other physicists, the Big Bang must have produced equal amounts of matter and antimatter. Yet the stars and galaxies we see across the universe are all made of matter. What happened? Why did matter win over antimatter? A new experiment aims to find out whether tiny particles called neutrinos might be the reason. Neutrinos are the most abundant matter particles in the universe. Trillions pass through us and everything else in the universe every second. They are produced in huge quantities in our sun and other stars, and in smaller quantities inside our Earth. Even bananas emit neutrinos. Scientists can produce neutrinos and antineutrinos with particle accelerators and study their properties in great detail. The Deep Underground Neutrino Experiment, DUNE, will test whether neutrinos and their antimatter counterparts behave differently. The experiment will be housed in the Long Baseline Neutrino Facility and use a particle accelerator at the Department of Energy's Fermilab. It will create the intense beam of particles that travel 1,300 kilometers through the Earth to the Sanford Underground Research Facility. DUNE scientists will build enormous, super-sensitive particle detectors while advancing state-of-the-art technologies. The detectors, located 1.5 kilometers underground, will catch neutrinos and antineutrinos as they arrive at Sanford Lab. The differences in the particles' behavior during their 4-millisecond trip from Illinois to South Dakota will tell scientists whether neutrinos could be the reason that the universe is made of matter. But DUNE can discover even more. If a star explodes in our Milky Way galaxy, the DUNE detectors will be able to see neutrinos from that explosion here on Earth. That will allow scientists to watch how the supernova leads to the formation of a neutron star, and possibly a black hole. The DUNE detectors can even look for particle tracks from proton decay. Many theoretical models predict protons are unstable, but fortunately for us, the average lifetime of a proton is very long, more than 100,000 billion years. However, a proton could decay at any given moment. If scientists observe it, they'll narrow down their models, moving closer to Einstein's dream of finding a unified theory of matter and energy. From neutrinos to black holes to proton decay, the discoveries made by the international DUNE collaboration will transform our understanding of the universe.
Okay, so let's review the video. I've done this in units of Nobel Prizes, which is as good a unit as anything. So this was the big claim here, was we have good reasons to think that the reason why there's matter at all in our universe has to do with funny properties of neutrinos. So it's not just that we think neutrinos are interesting, we think our existence may actually come from neutrinos. That's a strong claim, and it will require some very difficult experiments to understand whether that's, first of all, whether it's true, and if it is true, how that actually happened. And that's one of the big things we think that DUNE can contribute to. The second thing you heard is that when we have supernovas from exploding stars, that we will be able to observe neutrinos from those explosions with DUNE, and that's certainly the case. You do have to be a little bit lucky because we don't exactly know when the next supernova is going to go off, but in our galaxy, but I'll come back to that in a minute. There's just the fact that neutrinos are weird and surprising, and they may be connected to other, I already talked about a new force of nature that Fermi was the first one to talk about that has to do with neutrinos, but there might be other new forces of nature that have to do with neutrinos. And we just need better experiments in order to understand what's going on there. And then the third thing you heard about, this doesn't have to do with neutrinos directly, but just the fact that you've got these gigantic detectors. The detectors I was talking about for DUNE are 70,000 tons of liquid argon. So having really big sensitive detectors that just sit there for 20 years looking for neutrinos, it's also a really good way to test the stability of matter itself. And if you found out that ordinary matter is unstable, that would be a huge discovery. So that's basically what we're going for here. Here's a little bit more about the supernova. People make simulations for how stars explode as supernovas. We know that happens. There are supernovas in our galaxy happening probably every 20, 30 years. There's one. Some of them are more famous than others, but they're happening all the time. They're very complicated. It's actually very difficult to get a star to explode this way. In fact, it's only recently that we've had big enough supercomputers to make a simulation that actually makes a star explode. In the old simulations, the stars didn't explode because you actually have to put in a lot of the right physics before you can make them explode. And in particular, stars don't explode as supernovas in this particular way without neutrinos. And in fact, we think that something more than 99% of the energy of these kinds of supernovas actually come off in the form of neutrinos. And that's one of the things we'd like to understand better. That would tell us not only something about neutrinos, but also something about what's really going on in these catastrophic supernova events. So I think that's very exciting, and eventually we would be able to do that. There's actually already a supernova early warning system called SNOOS, because we already have neutrino detectors around the world, and the supernova might go off tomorrow, so we can't wait for the DUNE detectors to be ready. We don't know when it's going to happen. This is an example of a famous star that you've all seen in the night sky, Betelgeuse, which is close to going supernova, we think, where close means the next few million years. But still, it could happen tomorrow somewhere in our galaxy, and so we want to be ready for that. And Fermilab is part of this network with our existing neutrino experiments. So that would be very exciting. The other thing I wanted to close with is some of the things we're doing that aren't neutrinos. I've given you the impression that we're neutrinos, neutrinos, neutrinos. We're not. There's actually a huge amount of activity at Fermilab that has to do with other things. So for example, I already mentioned the Higgs boson. This was discovered at CERN, which is the European laboratory. These were the spokespeople of the two experiments that made the discovery, and this was in July 4, 2012 at the CERN auditorium. This is Professor Higgs, who won the Nobel Prize for predicting that the Higgs boson exists. He's talking here, this is the Nobel Prize ceremony the following year, and he's talking to, this is Marcela Carrena, who's one of our Fermilab theorists, who actually was one of the people that vetted his nomination and gave the green light that the guy deserved the nomination, so he's being nice to her. And this is Fabiola Giannotti, who is also in this photo. She led one of the experiments that discovered the Higgs boson, and in fact, she's now the Director General of the CERN laboratory, so very important physicist. And so that was 5 years ago. What are we doing now? Well, now we're trying to understand what these Higgs bosons are for and how they're connected to other things. And we don't understand how they're related to neutrinos. This Higgs boson, the force that goes with it, is related to giving things mass. But why do neutrinos have such tiny mass compared to other things? Does that have something to do with Higgs bosons being weird? We don't know. How are Higgs bosons connected to dark matter? If they have to do with giving things mass, dark matter has mass, so is there a connection there? We don't know. Is the Higgs boson related to the stability of the universe? There's actually a calculation you can do, and when I wasn't actually a theorist and had time to do this, I've actually reproduced this calculation. I wasn't the first one to do it, but it's a calculation you can do, which tells you that the Higgs boson makes the universe unstable in a fairly catastrophic way, which won't happen tomorrow, but if this calculation is right, it would eventually be the end of the universe, so it's kind of important to know whether that calculation is right. So we have many interesting things we want to study there. This we're doing not directly at Fermilab, but using the particle accelerators that are at CERN. And for that, we use these gigantic detectors. So these are not neutrino detectors. These are for detecting all kinds of particles that are produced in the collisions they produce at CERN. I don't even know if you can see a person here. So a person is sort of that size. This is the CMS detector, which is one of the 4 big detectors they use in the experiments at CERN. The reason I showed this one is because we're the host lab for the CMS experiment in the US, and in fact the spokesperson of the collaboration that runs this detector is Fermilab physicist. So we're very interested in this kind of physics. The reason this picture was taken is because we built some improvements to this giant detector that are being installed here that will make it even better for detecting Higgs bosons so that we can answer some of those questions that I was showing you. So that's a big thing that we do. It is literally a big thing that we do. This also involves computing, and it's really pushing the boundaries of computing. When you take the kind of data that we're taking already, for example, for these experiments looking at the Higgs boson, we've realized that although we have a lot of computers distributed around the world to analyze this data, we're about a factor of 100 short of what we're going to need to do the detailed studies of the Higgs boson that we're planning. So what are we going to do about that? We're not going to go out and buy 100 times as many computers as we have now because we can't get the money for that. And that wouldn't be the right thing anyway. So somehow we have to tap into somebody else that's got a lot of computers and have a system that involves that, that we can do our science in a way that isn't infinitely expensive. And we are in fact working with both Google and Amazon, who are building their own clouds for commercial use, in order to understand how we can take our fire hose of data coming out of these particle accelerator experiments and shoot them at Google and have Google help us analyze them. And this was a test. This is a live test that we actually did, showing that we could shoot our data at them at the rate of 243 teraflops without their clouds computers collapsing. Actually, they did collapse originally, and then they figured out how to handle the data. And they did this for free. They do this for free because we're really interesting customers to them because we're really demanding and challenging. And by figuring out how they can handle our data, they can figure out how to be more competitive for the commercial things they're doing. So just 2 more things. One, I mentioned dark matter. So that's most of the matter of the universe. It's even more important than neutrinos maybe, but we don't know yet because nobody's succeeded in detecting it. So what are we going to do about that? Well, we're actually part of 3 experiments that are running now. This is one of them, which is actually at the University of Washington, that are looking to directly detect dark matter particles in the laboratory. In some sense, it's the same thing I was talking about with neutrinos, but even harder, because if it weren't harder, we would have detected them already, because we've detected neutrinos. So these things are, in some sense, more difficult to detect than neutrinos, but we know they're there. There's dark matter particles in this room. They're traveling through all of space as we speak. So we need some kind of fancier detecting technology. This is one of the things we're working on at Fermilab. Is this actually is a superconducting circuit that was built to make something called quantum computers. I don't know how many of you have heard of quantum computers, but we believe that the future of computing may have to do with not the kinds of big computer hardware we've gotten used to, but with a completely different technology based on, if you like, nanoscale quantum technology. And what we realize is that these quantum computing technologies, because they're so sensitive, these are very sensitive atomic level quantum devices, they're actually very good candidates to make sensitive devices to look for dark matter. So this is one of the things we're working on at Fermilab. If you were a young person and you came to Fermilab and you wanted to work on something, this is the kind of thing we might put you to work on. And then last but not least, I mentioned dark energy. So this is not stuff, it's some kind of energy force that's out there, and I don't know anything more than what I just told you, except that it's affecting the expansion of the universe. But we think, again, by looking out with telescopes, in this case optical telescopes, at the whole universe, at all the galaxies in the universe, and studying all that in detail, we can maybe learn something about what's happening with dark energy. So for that, we actually built the world's largest digital camera. This is it, at Fermilab. This was using technology we had developed for particle accelerator experiments, but it works for telescopes. So this is on a telescope in Chile, on a mountaintop in Chile. And it is eventually going to image 300 million galaxies, and from that tell us something about dark energy. In the meanwhile, it already did something interesting. It saw this dot. So this dot didn't used to be there, and in fact, it's not there now either. It is in a galaxy. This is a galaxy that's 100 million light years away, approximately. And so they observed using this telescope that there was no dot here, and then there was a dot, and then the dot went away. And that was interpreted as something called a kilonova. And this is an explosion, a very particular kind of explosion that comes not from a supernova, but from the merger of two neutron stars. So these are two old stars that find each other and then have collapsed together onto each other. And the reason that we know that this dot was that and not something else is because at the same time that this happened, there was actually a pulse of gravity waves, which are distortions of space-time that were detected by a new observatory called LIGO. It's actually two observatories in two different places that has the capability to observe distortions of space-time of a particular type called gravity waves. So they saw these ripples in space-time, and they called up Fermilab and a bunch of other places and said, hey, we saw ripples of space-time. We think they came more or less from here. Why don't you guys go look at this galaxy and see if anything changed? And indeed, something had changed, and that was this explosion. So this is a whole new way of looking out at the universe, where we can look at the universe in light using conventional telescopes, but at the same time, we can get together with our friends that are looking at the universe in terms of distortions, ripples of space-time, and I think that's super exciting. It doesn't have anything to do with dark energy necessarily, but it's one of the most exciting things that we're doing at Fermilab. So I just wanted to close with quotes from two smart people. So this guy is Isaac Newton. This is something that he wrote at the end of his life, kind of humble. He said, I seem to have been only like a boy playing on the seashore while the great ocean of truth lay all discovered before me. So considering all the things that he did figure out, it's kind of humble to realize that he had only scratched the surface, which of course is true. He had only scratched the surface. And similarly with this guy, although he figured out a lot of things, he said, one cannot help but be in awe contemplating the mysteries of eternity of life, of the marvelous structure of reality. It's enough if you try merely to comprehend a little of this mystery every day. And I think both of these great scientists understood that it's not, of course we're trying to find the answers to these things, but every time we find an answer, we usually find a new mystery. And so in the end, we're really in the business of uncovering and poking at mysteries, and that's what we're really doing here. And I think it's good to think about this in that humble sense, that the universe is really much smarter and more complicated than anybody can understand, but we're getting at little corners and understanding little pieces of it all the time. So that's it. I just wanted to thank the people I plagiarized to make this talk, and thank you for your attention.
So we can have a few questions for Joe. Stand farther away from the speaker. And as usual, we like to prioritize the youngest questioners. Any of the, do you have any questions? I won't put you on the spot, but if you have a question, I'll come back to you. So let's pick somebody else. Go ahead and take you.
You say that the neutrinos rarely interact with other stuff. What is the result of the interaction?
Yeah, so in the kind of detectors I'm talking about, they actually interact with a nucleus, so say an argon. You have argon atoms, but there's a nucleus inside those atoms, and they actually give a little bit of a kick to that nucleus. And then that then produces what we actually see is we can see as a result of that kick, things happen in the argon. And the two things that we can actually detect from that is there's some electric charge that's liberated that we can collect. That's the reason we need to charge it up to 100,000 volts, so we can pull the charge out. And the other thing is it makes a little flash of light. And so we surround these detectors with light detectors in order to see the flash of light. So in the end, when I say we saw a neutrino, what I really mean is we pulled some charge out and we pulled some light, we saw some light. And from that, you then have a computer program with deep learning or whatever it is that tells you that was from a neutrino.
Oh, awesome. Here we go.
Okay, so if is there any telescopes to see a neutrino like with your eye?
Oh, very good. So I showed you what the sun looks like as seen in neutrino detectors. And you can also ask, well, could I see some of those other neutrinos that we think are coming in from the sky, like neutrinos coming in from the Big Bang, or neutrinos, you know, I talked about neutrinos from supernovas, but there's supernovas all in the universe producing neutrinos all the time. So can I see any of those neutrinos with telescopes? And the answer is probably yes, and there are some people working on that, and it's really hard. And in fact, this guy standing on the stage is one of the people that's had the ideas that we're now using to try and do what you're talking about, which is to see some of those other neutrinos coming from space.
How about?
So, do neutrinos have any charge on them, like themselves, like positive or negative?
Yes, they don't have electrical charge, but they do have, if you like, a charge under that weak interaction that Fermi invented. And in fact, that's the way we make them. They're made from the fact that they do interact a little bit with ordinary material, but the reason he called it a weak interaction is because it's really weak. So compared to electrically charged particles, it's like almost nothing.
I'm assuming I'm not the first person who's noticed that when you discuss these having a slight mass and some other properties that they kind of fit the definition of a wind when talking
Yes.
about dark matter.
Yes.
Repeat the question.
So, so neutrinos sound kind of like what you were talking about with dark matter, and so could they be dark matter? And in fact, when people first realized that there's all this dark matter out in the universe, the first papers that people wrote on it were, okay, well maybe it's neutrinos, maybe not the neutrinos we've already found, but some other kind of neutrino. Maybe it needs to be a little heavier neutrino or whatever. And so that indeed was what people pushed, and that was seemed like the simplest explanation. It actually took quite a bit of evidence of looking in detail out at the universe to prove that most of the dark matter is not neutrinos. If you like, you could say 1% of it is neutrinos, because we know there's lots of neutrinos out in the universe and they do have mass. But took a long time, I'm talking decades really, to prove that the dark matter, whatever it isn't just neutrinos, it's some other thing.
Why don't you go ahead?
You describe gravitational waves as like ripples through space-time. How would you define space-time? Is there any sort of like definition?
Well, yeah.
First, try to repeat the question.
So the question is, what's the definition of space-time? So what's the definition of, let's do space, because forget time. So what's the definition of space? So, so this is a philosophical question that goes back hundreds of years. I mean, Immanuel Kant said, you know, there are certain things that are just there, and then everything else is sort of you put that in the there. And so space was an example of that, he said. It's just there, and I'm not going to explain that because that's sort of the theater, that's the stage on which I explain everything else. So that's one explanation. I think a more modern view is that space is also a thing, and it has properties. And part of what we're doing in particle physics is trying to understand what the fundamental properties of space are, and eventually time as well. We think that space probably isn't smooth. So even when I talked about ripples, it sounds smooth, right? It sounds like space is like a body of water or something. We think that's probably not true, in the same sense that if you look at water and under an electron microscope, you realize it's a bunch of atoms. It's not really smooth. We think that's probably also true of space, but it's much more difficult to do that experiment for space. So it's an open question.
Put it back there.
In your talk, you mentioned different ways neutrinos can be produced. Can neutrinos decay, or are they just?
Yeah, so this is something that we've looked at in experiments. Neutrinos could, in principle, decay, and it's something we've looked for and we haven't found. You can also ask this for neutrinos out in the universe. How would the universe look different if neutrinos decay? So far, the evidence is that neutrinos don't decay often enough, at least, that we would have seen it in all the things we've looked at. But it's still an open question. I think for any elementary particle, it's always a fundamental question. Is there some other lighter? Has to be something lighter to decay into, right? Obviously. But other than that, it's always an open question.
Go ahead, sir.
A while back, there were articles in the paper that people were afraid that you guys using these accelerators were going to destroy the universe. What was that about?
Yeah, there was, this is one of my favorite articles in The Onion, the satirical newspaper, The Onion. You can look this up. It says, Fabiola Giannati, who I mentioned, Director General of CERN, apologizes for accidental destruction of 6 parallel universes. The particular complaint had to do with the fear that we would produce microscopic black holes from particle collisions in one of these particle accelerators, like the LHC at CERN, or we had an accelerator called the Tevatron at Fermilab, which you could have worried about that as well. And that once you made these microscopic black holes, that they would just start to accrete matter. They would suck in, everything in your lab, and then everything in Batavia, Illinois, where Fermilab is, and then Chicago, and then you guys would be next. So that was the fear. There are lots of good reasons to think that that can't happen. One of the reasons is that nature has particle accelerators. When I talk about cosmic rays, those are very high energy particles that nature made out in our galaxy or somewhere from natural processes. We know that those particles are at much higher energies than what we can make in the laboratory. So if that was making black holes that suck up the Earth, why are we still here? So I think that's the strongest reason. But we actually made a task force of people that was based at CERN to go through the whole argument just to make sure there weren't any loopholes to worry about.
How about you, ma'am? Go ahead.
Saying that there is a lot of neutrinos or locals that we get hit by
Yes.
come across here more often than others. Are there any biochemical or biological effects of this? Or are there any antidotes if there is some
It's, as I said, maybe one person in 4 in this room will have a neutrino interact with them in your entire lifetime. Let me compare that with ordinary cosmic rays. There's charged particles coming from cosmic rays going through this room right now. You're being hit by several of those per second. Those do have biochemical effects. They cause cancer. So ordinary cosmic rays that you can't do anything about unless you go live in the Homestake mine, a mile underground. They do have effects on biology, some of which are harmful. But that effect is trillions and trillions of times greater than the effect of neutrinos. So neutrinos are just, forget the neutrinos. It's the cosmic rays you should be worried about.
But not that worried.
But not that worried.
How about you in the front there?
Okay. You mentioned that neutrinos can travel through the Earth while rarely interacting with them. Would it be possible to create a stream of neutrinos to be used to communicate through the Earth?
Yes. So this was seriously suggested by some people. Suppose I want to know what happened on is it Shanghai or Beijing where they have the stock market in China? Let's say Shanghai. I want to know what happened in the Shanghai stock market, and I want to know 1 millisecond before everybody else knows in New York, so that I can sell something. Right? In principle, neutrinos are the best way to do that because they go straight through the Earth. So we actually demonstrated, some Fermilab physicists demonstrated with our existing experiments, which go over hundreds of miles, that you can actually send a signal like, sell, sell, sell. You can actually do that using neutrino beams. The problem is that the neutrino detectors that we have now are very slow to operate. And so you lose that millisecond in the fact that the detectors take a long time to read out what happened with the neutrino. But that's just, that's a technological detail. So I think eventually somebody could figure out a way to do exactly what you're talking about.
You just find a way to fund Fermilab forever?
Yes.
He's a genius. Let's take one more question. Let's see. How about you?
In regards to the DUNE experiment with neutrinos and antineutrinos, I was wondering if you had any interesting predictions for the results?
Yes.
Maybe repeat the question.
So the question was, we said that we're going to study neutrinos and antineutrinos to try to understand this question about the origin of matter. What's my prediction for the result? So my prediction is that we are going to find that there's a difference between neutrinos and antineutrinos, and furthermore, eventually understand that that's the reason why we're all here, the reason why matter exists at all in the universe. The reason I think that is just by looking at the alternative explanations. So this is something I have actually worked on in real life. And there are other explanations that don't involve neutrinos, but those explanations, first of all, made at least one set of explanations made predictions that have been shown to be false. So that doesn't always discourage theorists because we can go back and tinker with the theory a little. But nevertheless, the other explanations have had a chance to be vindicated, and so far don't look that good. Whereas everything we know about neutrinos is very consistent with the idea that they're the reason we're here. So that's my guess, but of course, guesses are not good enough in science. You have to do the experiment.
So to wrap up, I'd like to thank everybody for their time, interest, and attention, not only today, but over the course of the Science Sunday series. The high level of interest is why we're able to attract great speakers like the Deputy Director of Fermilab. And if you're not already signed up for the Science Sundays email list, I encourage you to do so. About once a month, you'll get an announcement of events like this. Now we'll go upstairs. There'll be a nice reception with nice food and drink, and you'll have a chance to ask Dr. Lykken further questions. Let's thank him.